And we welcome you to Lesson 6 in Math 222. We are going to take a look at L'Hopital's rule, named after the very famous mathematician L'Hopital, but originally propounded by John Bernoulli. And that's a whole story in and of itself that we won't tell in this screencast. This lesson and the next lesson use L'Hopital's rule to evaluate limits. Limits were those things that you learned at the beginning of Calc 1 and forgot how to do right after the first test. So I've got to bring them back with a twist. And so let us consider the rule. This is L'Hopital's rule. And my French minor will require me to put l'accent circumflexe right there. Goes like this. Suppose that f of a and g of a are both 0 for some a in the domain of both of those functions, that f and g are differentiable, which you will remember from Calc 1 implies they are continuous. So not only are they continuous, they are differentiable on an open interval I containing A. Containing a what? No, containing this A. And you have to further suppose that G prime of A is not 0 on the whole interval except maybe at A. Then the limit as x approaches A of f of x over g of x is the limit as x approaches A of f prime of x over g prime of x if the latter limit exists. The heck does this say? Okay, so I go back to Calc 1 and I try to remember from Calc 1 how we did that. Well, in Calc 1, we did that by sticking this A in both of those places. So you take that A and you stick them in there because, of course, all functions are continuous. And, in fact, f and g are continuous. So you take this A and you stick it in both of those spots. You get f of A, you get g of A. But wait a minute. F of A over g of A, that's 0 over 0. Well, we don't know what 0 over 0 is. So L'Hopital's rule says take f prime over g prime. This is not quotient rule. This is f prime over g prime. If that limit exists, it's the same as the one you want. Now, that's a little bit weird to think about. But consider the following. Bill Nye the Science Guy. So that's A. And you have two functions, and they're both 0 at A. And you're trying to figure out what happens when you divide the red one by the blue one. This is the blue one, this is the red one. And it's awfully hard to figure unless you remember that these functions are differentiable. And differentiable functions are locally linear. They are smooth functions. And since they are smooth functions, what we can really say is right around here, the tangent line does the job. Right around here, the tangent line does the job. And so we're going to compare the slopes of two tangent lines, and if that works, then we say that the original limit has the same value. The proof itself goes far beyond the scope of our course, but this is the general idea. We're going to take a look at functions that are differentiable as locally linear and use their tangent lines to approximate the functions in a small interval. So what does that mean for you? That means we can find things using L'Hopital's rule that we used to have to do tricky things to find before. If you were to pull out your Calc 1 notebook, you would find a question like this, and you would find that your teacher multiplied and divided by a conjugate because the numerator goes to 0 and the denominator goes to 0, and you said 0 over 0, what do we do? Well, we'll multiply and divide by the conjugate, and some funny things will cancel out, and we'll make an algebraic mistake, and then we'll know sort of what the limit is. But L'Hopital's rule says that this limit is the same as the limit as x approaches 2 of whatever the derivative of the numerator over the derivative of the denominator is. I'll do the derivative of the numerator. That's 1/2 times this to the negative 1/2 times 1, but that's not relevant. You do the derivative of the bottom. Anyone? Anyone? Good. Okay. So there. So now we try again. So we try again. Can I substitute that 2 in there? Sure I can. That's 4 to the negative 1/2. 4 to the negative 1/2 is 1/2 times 1/2. That's 1/4. L'Hopital's rule says if this limit exists, it is the same as that. Limit x approaches 0. 1 minus cosine x over x squared. Again, a scenario where as x approaches 0, oh goodness, cosine of 0. Nobody remembers cosine of 0. Yes, we do. 0 squared, that's 0. 0 over 0, what do we do? That's an indeterminate form. No one can know. It's impossible to know. Okay, fine. L'Hopital's rule says this function is smooth, this function is smooth. So instead, take the derivative of the numerator and the derivative of the denominator and try again. So x approaches 0, so this goes to 0, and this, golly, rats, okay. But wait a minute, this is a 0 over 0 limit, so L'Hopital's rule says that I can use L'Hopital's rule on this limit. So I'll just use L'Hopital's rule again, take the derivative of the numerator and the derivative of the denominator, and try again, x at all. So as x approaches 0, that's 1/2. L'Hopital's rule says if this limit exists, it's the same as that one. If this limit exists, it's the same as that one. That's the one we wanted, 1/2. I hope that's okay. I hope this is like the easiest thing we've done all semester. I really do. So how about that? Well, is that doable? Well, I hope it is. L'Hopital's rule says that this is the limit as x approaches 0 from the right of secant squared x over 2x. So as x approaches 0 from the right, the numerator approaches 1, the denominator approaches 0. Now, we're approaching 0 from the right, so these are teeny tiny numbers that happen to be positive. So you take 1 and divide it by a teeny tiny number that's positive, you get positive infinity. And L'Hopital's rule is A-OK. Side note, this also holds for indeterminate forms of that form, infinity over infinity. I'm going to ask when we gather why you think that holds. See, the 0 over 0 thing is okay. We can sort of generate that. But I'm saying based on this discussion, it is not inconceivable for you to think about why this is true. It is not inconceivable for you to think about why that's true. But I will demonstrate it. Take a limit as x approaches pi over 2 of 1 plus secant x over tangent x. And this is just blatantly so I can get trig in there. Both of those approach infinity as x approaches pi over 2. So what does that mean? It means we take the derivative on top and bottom. On top and bottom, the derivative on top is secant x tan x. The derivative on the bottom is secant squared x, and surely this can simplify. I don't need L'Hopital's rule here. I need a little bit of trigonometry here to know what tangent x over secant x is. Well, I know that this is sine x over cosine x, and this is 1 over cosine x. So I don't need L'Hopital's rule. I just need trig. Sine x over cosine x over 1 over cosine x, those go away. You get the limit of sine x as x approaches pi over 2, and that's 1. Fair enough? Excellent. Well, you're almost done. Just a couple of things for you to consider before we gather. You should know before we gather in class how to find this limit, which you would previously have had to do with some crazy algebra. And what about this limit? Again, both of these functions grow infinitely large as x gets infinitely large. Both of them look like they should have some horizontal asymptote. They don't. But which one grows faster and how can we talk about that? Those are some things to consider for when next we gather. All right, very well. That's the big topic for our discussion next time. Looking forward to seeing you.